In this unit, we'll cover why we need to generate broadband material fits in the first place. For dispersive materials, we have the frequency domain relation d equals epsilon times E, where d is the displacement field, epsilon is the material permittivity, and E is the electric field. Since FDTD is a time domain solver, we need to convert this relationship to the time domain, where the multiplication from the frequency domain becomes a convolution product in the time domain, which is an integration over all previous time. The permittivity over time is what gets simulated. To perform this integration by brute force at each time step in the simulation would require more time and memory than would be practically feasible. But it turns out that for a certain set of functions, there are known solutions that don't require performing the integration, so it's much more computationally efficient. However, there are some restrictions to the types of functions that can be solved, and these include restrictions due to stability and causality. For example, you can't have a result at a point in time depend on an electric field from a future time. This places some restrictions on the relationship between the real and imaginary part of the permittivity, known as the Kramers-Kronig relations. Similar restrictions apply to conductive material models. Before running broadband simulations, a broadband material fit is generated which meets these restrictions for dispersive materials. For imported data in sampled data materials, the broadband fits that are generated use the multi-coefficient model, or MCM, which meets the required restrictions. The multi-coefficient model is able to generate good fits for a broad range of dispersive materials like the ones shown here, and the material fits to data often better represent the real material properties compared to using simpler materials like the Drude model, also known as the plasma model, for metals.